Hey gang, this time you get to look at me, not at the, or you don't get to look at me, you get to look at the screen. So I wanted to do a quick finish of the lecture that we did on Thursday so that you have all the information you're going to need to do Stats Lab 2. It is my every intention, unless something strange and unprecedented happens, to have Stats Lab 1 due by, or have Stats Lab 1 graded by Tuesday's classes. So if you're at Tuesday's classes, you can ask me questions. And then again, we'll put up Stats Lab 2 by about 5 o'clock on Tuesday. And then you will have a week, you will have 90 minutes to do it. You will have a week window in which you can do the Stats Lab, and we'll be off. So when I last talked to you on Thursday, we introduced regression analysis. Regression analysis allows us to establish causation, and it does it through, remember that equation that I put on the board, which is the equation for a line in algebra 1 or 2 or whatever it is, which is y equals mx plus b. SPSS basically uses that logic to help us figure out the effect of one independent variable on another dependent variable. Remember, all we're trying to do, you see the scatter plot right here, right? You see the scatter plot, and all SPSS is doing is fitting the best possible line into this graph. And by fitting, I mean, what's the line that best describes the relationship between the dots here? Okay, so I first showed you how to do a relationship between one variable and another, between one independent variable and one dependent variable. So we'll go in here, we'll go into regression, we'll go into linear, and we're going to go back to the example that I used the other day. I'm using, by the way, the states data set. And so let's say that the outcome we want to predict, our dependent variable, is not women legislature. It is percentage of the population in a state that has a college degree. And then the independent variable, the thing that we think is related, is the percentage of female legislators. So what we're asking right now, we are testing a hypothesis that says, okay, what is, we believe that as the percentage of female legislators in a state increases, it will increase, it will cause an increase in the percentage of a total population that is college age. So I've got this set up, and this should all look familiar to you. And what we can see here, right? First two things that I wanted you to look at. So thing number one that I wanted you to look at was the test of significance. We always do this with any statistic. We look at, first off, is the result real? And so we're going to look at this column to the far right. And it says, yes, we read this exactly the way we read the significance, the sig2 tailed test and our correlation coefficients. And that says, yes, we have a significant relationship here. And so then we go over, I need to scroll down a little more here. I'm looking at the wrong thing. So that's what I want you to look at, right? A regression analysis in SPSS will spit out 3 tables at you. Look at the bottom one first, all right? So you're going to see the statistical significance for the coefficient that you care about is 0.000. Read this exactly the same as a sig2 tailed test and a correlation coefficient. So this means we have at least a 99.9999% chance that we're observing a real relationship. Then look at the unstandardized coefficient. All right, what the unstandardized coefficient will tell you is the impact of a 1 unit move from the independent variable on the dependent variable. So in this case, what SPSS is telling us is that for every 1% of a state legislature that is female, okay, it will equal another 0.358% of a state's population that has a college degree. And again, this is all stuff that we did on Thursday, okay? But now, the really nice thing, the really neat thing, really interesting thing with SPSS and with regression analysis as a whole is that we can actually see, we talked about what's the problem here, all right? And the biggest problem that we see here is that we do not have, we think that there are we know that there are going to be other things that contribute to what percentage of a state's population is female, right? There are, oh, I am just having a wonderful day already. We know that there are other things that contribute to whether or not people get a college degree, not are female, all right? There are all different factors that we think might determine whether or not a person goes to college, finishes college, gets a degree. Regression analysis can look at that, okay? So, I'm going to go to regression. I'm going to go to linear. And now, I am going to add in a couple more factors that I think may impact whether or not the level of a state's population that has gotten a college degree. So I'm going to throw in the percentage of African American residents. I'm going to throw in the Hispanic, and I'm going to throw in elderly. All right. Now, then we hit OK. And we're going to scroll all the way down. Now, what you see here, all right, is you see that each of those independent variables that we threw in has their own statistical significance coefficient, okay? So we still see that female legislatures has a significant impact, okay? But look at this. All these other three, our BS meter is well above the 0.2 threshold that we established for this class, right? So that means that we cannot take any of these as having a real relationship with the dependent variable, with the percentage of a state's residents that have college degrees, okay? Now, so we know that those don't matter, okay? But they do matter in a really important sense. You'll notice that the coefficient has changed here, okay? So now, for every percentage of a state legislature increase that is female, we get an additional 0.381% of a state's population that has college degrees, okay? What's neat about regression analysis is that it simulates a condition in which we see what happens when this variable moves 1 unit and these are all held constant, okay? So in other words, in this model, we have controlled for black, we have controlled for Hispanic, we have controlled for 65 and older, okay? And so that effect that we see there, basically we know that it is that effect works even considering all these other factors, because we've controlled for these other factors. It's like we created two states, all right, that are exactly the same, have exactly the same percentage of their population that's black, exactly the same percentage that is Hispanic, exactly the same percentage that's 65 or older, all right? We created two states that are exactly the same across those three dimensions, except one of them has 1% more of their state legislatures be female, all right? So in other words, this is what I mean when I'm talking about the causality that regression analysis helps us establish, okay? Because, oh, this is so tricky and beyond me. Because we can introduce controls, we can now start to see what the relationship is between an independent-dependent variable, what the independent effect is. And by the independent effect, I mean what is really what's really the difference that female legislators make, even when we have these things controlled? So basically, through regression analysis, statistics allows us to create an artificial lab setting. It allows us to create an artificial experiment. We're not actually conducting an experiment here. We're not bringing people in. But we are simulating experimental conditions using math, basically, using statistics and all that stuff. I could talk about how that works, but I don't really think that that's important. All you need to know is that these coefficients, when you have more than one independent variable, if these coefficients are statistically significant, that means that this is their effect when all the other variables in the model are controlled for. Okay? And that would be true for any of these. Say, for example, that the percent black, all right, say that that was statistically significant too, that had a significant coefficient of like 0.07 or something, okay? So this would be statistically significant. That would mean that this would be the effect of a 1% move in the black population, a 1% increase, even if female legislators, percent Hispanics, and 65 and older were all controlled too. So this gives you the regression analysis with more than one independent variable yields the independent effect of each independent variable in the model. Okay? Now, I told you on Thursday that there were 3 things that I wanted you to look for, okay, in this SPSS regression table. All right? First thing that I want you to look for is the statistical significance of the various coefficients. Second, if for all the variables that have a high or that have the right statistical significance, I want you to look at the size of their coefficients. The third thing that I want you to look at is in this first table right here, and it is the R squared. Okay, so that's the third thing, the R squared. Let's talk about what the R squared is. And to do that, I'm going to scroll back. If you were in class on Tuesday, or on Thursday rather, you remember me putting this chart up the board, right? And you remember me from the beginning of this little video, right? You remember that I said that what regression analysis is doing is really drawing a line through here, the best possible line that depicts our, that describes our data, all right? But, right, you can see that no matter what line we draw through here, we're not going to explain everything about every data point, okay? So, we're drawing this line right here, and that's a good measure of central tendency, but it doesn't tell us where each point on the line is because it doesn't tell us where each point is because each point doesn't fall on the line. So what we need, right, is we need a statistic that says how good our regression model is. Tells us we've got these 4 independent variables in the example that we just used, okay? What we would like is a statistic that tells us these 4 variables right here, right? How much of our dependent variable do they explain? In other words, if we know a state's, if we know a percentage of state, if we know how many females are in a state's legislature, the percentage of its black population, the percentage of a Hispanic population, the percentage of its age 65 or older, if we know those 4 things about a state, how likely are we to be able to predict what percentage of its population has a college degree? Okay? How much do these 4 factors explain the percent of a state's citizens that have college degrees? So in this case, right, that's what our r squared is. Our r squared, the range is from 0 to 1. As it gets higher, that means that we've explained more. Okay? So, this raises the question, right? So 0, if we have a 0 r squared, it means that our variables down here tell us absolutely nothing, okay, about the dependent variable. If we had an r squared of 1, what this would mean that is if we knew these 4 things, we could predict, and if we knew these 4 things about any state, we could predict the percentage of their population that has college degrees with 100% accuracy 100% of the time. These 4 things would tell us everything we needed to know to make completely accurate predictions, okay? We have an r squared for this model of 0.36, okay? Now, that raises the question, is 0.36 an r squared? Is 0.36 a good r squared? Well, so on one hand, you might say, all right, we know 4 factors, and that only explains 36% of the outcome. Well, that doesn't really seem all that good, right? 36% is not a great level of prediction, okay? But not surprisingly, since we in the social sciences deal with weirder situations than the hard sciences, all right? 0.36 is not a terrible r squared, and here's why, all right? If we know these 4 factors, we know 36% of the reason, 36% of what we need to know to accurately predict a state's college population with degrees, all right? That means that just these 4, there are 100, there are 1,000, there are 1,000,000 factors in the world that determines whether or not somebody gets a college degree. If we can just, with 4 of them, predict 36%, we're doing a pretty good job, right? Because remember, again, people are idiosyncratic. There are all types of ways, reasons, factors that matter for why people get college degrees. But if just knowing these 4 things gets us a third of the way to making prediction, in other words, we can make accurate predictions for a third of the states, then we can concentrate on some other factors and start to know what's going on there too. Okay? Trying to think of what else that I want to say. All right, let me go over really quickly the advantages and disadvantages of regression analysis. Okay? So the number one advantage here is that this math that we're doing here, or that the computer's doing for us, is moving us towards causality. When we control for other factors, we move towards the elimination of spurious relationships. We start to figure out that, okay, no, it's not a third factor that matters here. I know that percentage of state legislatures who are female matters to college degrees, even when I have these other 3 things controlled for, all right? And when you can rule out other explanations, you start to move towards causality, okay? Regression analysis also creates a situation where we can say how much our independent variables impact the dependent variables. So based on our model right here, right, we can make a strong prediction that in the past, whatever year this data set was for, right, a 1% movement of female legislators was equal to a 0.381 increase in the college degree population in a state, okay? And so that's really powerful. We can start to understand not just like, is there a relationship, but how strong is that relationship? What does that relationship actually mean in terms of real things we might see, okay? Now, regression analysis and other multivariate techniques are not perfect. And I want to talk about some problems here, all right? So everything that we're doing here, the first problem that I want to bring out, right, is that this is kind of artificial, right? So we're blocking off the world and we're just determining, let me start again, okay? this is kind of artificial, all right? In life, we don't have nice controlled settings where we can make everything stay the same, where we can create conditions like these, all right? More importantly here, we might also expect that changes in one independent variable don't just cause changes in the other dependent variable, right? So one independent variable may also affect the values of another independent variable. We call this an interaction effect, all right? So it could be, right here, let's take the percentage of people 65 and older. That does not have a statistically significant effect on the dependent variable. But it could be, right, that the percentages of elderly has an impact on the percentages of state legislators who are women. Let's say, right, that as this increases, right, as we got more older people in our population, they're more traditional in their social values, they're less likely to vote for women, all right? Our model's not going to capture that. So there's clearly something going on about being elderly that is contributed to the outcome, but our model doesn't do that. Instead, it attributes whatever the effect of older is to this variable, when really the causal relationship goes independent variable to independent variable, this independent variable to dependent variable. Now, there are ways to get around those, but it's something you need to be aware of. All right. Other thing I want to bring your attention to is our low R-squareds here, right? I told you the 0.36 is a pretty good R-squared in the social sciences, and it does. It does mean that this model tells us something. However, right, we're still only explaining 36% of our dependent variable. So that's to say we get these four things, we're 36% of the way to predicting the dependent variable. That's not great, right? We would like to be a whole lot more sure about things, all right? And in fact, in the social sciences, whenever we're dealing with truly interesting phenomenon, truly interesting stuff, our R-squareds are going to be kind of low. And what that means is it's very important for us to recognize the limits of our model, okay? So in this case, we can be reasonably confident that this matters, all right? And we can be reasonably confident in this prediction. But we also have to take into account the fact that we're not explaining that much. So let's not go wild with how strong we think these conclusions are, all right? And people get into this problem all the time, right? You put it in numbers, it looks very convincing, and it looks very distinguished, very serious, very like matter of fact, right? But in fact, when we have low R-squareds like this, we need to be conscious that we haven't explained everything, and that opens up the potential for a lot that we can't explain. A related factor here, right, is the existence of black swan. The model that we're looking at right now only tells us the factors that mattered in the past, okay? As we get a better sample and we choose better variables, we may be able to increase this R-squared, right? But we're still only explaining the past. And if there's one thing I hope that I stress to you guys this semester, it's that the past is helpful for telling us what will happen in the future, but it is not 100% ironclad, okay? Black swans do happen, all right? And black swans, what you're looking at here, can explain everything you need to know about why the financial crisis happened in 2008, okay? Remember, we went over this at least once. All the wealth that was lost in 2008 had been created based on bonds that were created out of home prices, okay? So in order to sell those bonds, people needed to know what the risk was of those bonds collapsing, all right? In order to come up with a risk rating, some very smart people came up with really advanced, far better than anything I could do, models like these, multivariate models. And what they wanted to predict was housing defaults, because they figured, okay, if we can predict how likely someone is to default on these mortgage-backed securities, we'll be able to tell you the level of risk that your bond will be worth less than you thought it would be. Okay? It was ironclad in like that. That way, it makes it sound ironclad. So they developed all these things. What they lost track of was this R squared, right? I bet you that they came up with really high R squareds. I bet you their R squareds were like 0.9, right? And 0.9, you can explain 90% of something. That's really good, right? But one, that still leaves 10% unaccounted for. And two, right, they were basing it off of history, all right? And they were basing it off a 20-year history, and they made a graph, they made a model that almost perfectly predicted that 20-year history. But the future is not necessarily exactly like history, right? And so what happened was a black swan happened, and then all of a sudden these variables, they didn't explain enough about the current condition. The world had changed and left their model, kind of worse than useless. So it's important to remember, right, that when we do this multivariate modeling, it is a great way to simulate experimental conditions, to create experimental conditions out of the past that might give us some guidance about what happens, okay, in the future. But we always have to be humble and recognize that that the conditions in the world may change and that our model may not apply. We'll pick this up again on Tuesday for those of you who are there. Thank you very much.